All right, here we go. So we were doing Diels Alder Reactions on Friday, right? And so we were doing stuff like this. Oops, too many carbons. There you go. All right. So we need to be able to go from here to the product, right? And again, since we're doing a Diels Alder reaction, we know that we're always going to get a cyclohexene. And we know based on how we number these that our double bond is always going to be between carbon 2 and carbon 3. Right, so carbons 1 and 4 each have a methyl group, so they each need to have a methyl group in the product. Carbon 2 and 3 also have methyl groups, so they need methyl groups in the product. We have a nitro group on carbon 6 and a methyl group on carbon 5. Okay, same thing down here on the next one. Diene, dienophile, some heat. You know you're doing a Diels Alder reaction. All right, so carbon 1 has 2 methyl groups on it, so we need to have 2 methyl groups on carbon 1 in the product. I don't know why they're blue. There we go. 2 methyl groups on carbon 1. Have an ethyl on carbon 4, and methyl on carbon 2. And then 5 and 6 each have an aldehyde, so 5 and 6 are each going to have an aldehyde. As far as so good? All kind of rings a bell, hopefully, maybe. So, as we pointed out on Friday before we left, right, that we're making chiral centers when we're doing these reactions. So if we look at the top example here, carbon 1, 4, 5, and 6 are all chiral. So it would be nice if we could predict the stereochemistry we were going to get in our reaction, right? So we knew what we're gonna end up with. So we're going to switch into stereochemistry. Or Diels Alder reactions. And this is going to, we're going to look at two things. First, we're going to look at the diene. Right, so the positions of our groups on carbon 1 and 4 determine the relative stereochemistry, right? So how these groups are arranged on the end are going to determine their stereochemistry. So the double bond geometry of the diene gets transferred into the R and S, or the relative stereochemistry, the cis and trans of the ring. So what I like to do, the easiest thing I have found to do, is if you take your diene, and I like to say that my diene makes a box. So if I draw my box in here, right? I look at the two groups as being inside or outside the box. So here, both groups are outside of the box that my diene makes, right? So if they're both outside, I'm saying they're on the same side, and that side is outside, right? Right, so both groups are outside the box, they're on the same side. So they're on the same side of the diene, outside, which means they're going to be in the same side of the product. So if both your groups are outside the box that your diene makes, they're going to be on the same side of your product. So they can both be up or they can both be down. All we know is that they're on the same side. So they're either both wedges or both dashes. So I have the both outside example. And then I can have my groups be on opposite sides. So you're going to have my box. But here I have one group outside my box and one group inside my box. They're on opposite sides. So they're opposite. Inside, outside, opposite. So they're going to end up on opposite sides in my product. So you just look at the groups at 1 and 4. You decide if they're both inside or both outside. And that will give you your stereochemistry. So again, we're doing a Diels Alder reaction, so we know this is our product. So we have the groups on 1 and 4. Are they on the same side or on opposite sides? Opposite. One's outside, one's inside. So one's a wedge, one's a dash. Now, I'm not right now going to worry about the chiral center on carbon 6. Not an issue right now. So we know the relative stereochemistry of 1 and 4. We're not going to worry about 6. So down here, are they on the same side or on opposite sides? Same side. They're both outside the box. So they're going to be on the same side. I like to draw wedges all the time. If you're a dash person, that is perfectly fine. As long as they're both on the same side, we're good. Again, I'm not going to worry about stereochemistry on 5 and 6 right now. We're just going to put the groups there. You can have more than one group on your carbon 1 and carbon 4. All right. So if we look at carbon 1, it has two different things on it, right? But what you're going to do is you're going to compare each thing to each substituent to the group on carbon 4. So if you look, the methyl group on carbon 1 and the methyl group on carbon 4, are they on the same side or opposite sides? Same. They're both outside, so they're going to be on the same side. So we can be like, this is a wedge, and this is a wedge. Now the ethyl and the methyl, they're on opposite sides, right? The methyl group's outside the box, the ethyl group is inside the box. So if I've said the methyl group on carbon 4 is a wedge, that means the ethyl group on carbon 1, to be on the opposite side, has to be a dash. Right, so you're just comparing each group. And then again, carbon 6. Now this last one is the one that you never ever get. And this doesn't react. So you never have to worry about if your two groups are both inside on the diene. The reason for this is that there is a steric interaction. Those two methyl groups bang into each other. All right. So what that does, I'm going to go to the other slide. I'll give you a sec. So these two things bang into each other, which causes the diene to rotate around the single bond. Right? And now the two double bonds aren't on the same side anymore. So to do a Diels Alder reaction, right, if you think about it, your diene is 2/3 of your ring already, right? It has 4 of the carbons that you need, and it's kind of like this. All you need to do is put 2 carbons in, and you make your ring, right? If I rotate it so that the two double bonds aren't pointing in the same direction, I'm really far away from making a ring, right? Right? This looks like almost a ring. This doesn't. So this is called the S-cis conformation, where the S stands for sigma, or single, you can think of it. Is what it's saying is that the double bonds are on the same side. Right? And so the double bonds are on the same side of the single bond. This is S trans. Right? S trans, the double bonds are on opposite sides of the single bond. S cis, S-cis conformation, that can do a Diels Alder reaction. S-trans, no Diels Alder reaction. So you have to be in the S-cis conformation to do a Diels Alder reaction. And if you have both your groups inside your diene, there's so much steric interaction that the molecule flips and becomes S-trans, and then S-trans can't do a Diels Alder reaction. This is the long explanation for you only have to worry about the groups on 1 and 4 being both outside the double bond, or one being outside, one being inside, it never happens if they're both inside the double bond. Make sense? The other thing to keep in mind is that carbons 2 and 3 in the product can never have stereochemistry, right? Double bonds don't have stereochemistry, they're flat. So you can't ever put a wedge or a dash on carbon 2 or carbon 3. You just can't do it. So you can say, okay, carbon 1 and carbon 4, those are on the same side, they're both outside, right? 2 and 3 are just going to be, are going to have ethyl groups that are flat, no wedges or dashes. So like the one bright side that COVID has given you as it has wrecked the whole world is all your exams are multiple choice, which means you don't have to just draw the products from nothing. Because I guarantee you, at least 2 people would throw some very sick wedges and dashes on carbon 2 and 3 and then get it wrong. Right? It'd be like, oh, stereochemistry, let's throw some stuff on there. Right? So you kind of get like training wheels. So you never have stereochemistry here because it's on a double bond. So it's just always flat. So that is your diene side. What about stereochemistry for the dienophile? So if it's cis, if they're on the same side, they end up on the same side of the ring, both wedge or both dash. If they're trans, you'll end up with them being trans in the ring, one wedge, one dash. So you've got your diene, right? Here, the two groups on your dienophile are cis. They're on the same side of the double bond. Right, so they're either going to both be a wedge or both be a dash, but they're going to be on the same side. Here they're trans, right? So they're going to end up on opposite sides. You're going to have one group a wedge, one group a dash. And again, we don't know which one's which. All we know for sure is that they are on opposite sides. So you can put all of this stuff together, right? You can do diene and dienophile and have stereochemistry for both. Right. But what I do for these is I do a little bit of a cheat. What I have you do is I have you determine the relative stereochemistry on carbon 1 and carbon 4, ignoring 5 and 6. And then I have you do the relative stereochemistry on 5 and 6, ignoring 1 and 4. So what I mean by that is 1, 2, 3, 4. The groups on 1 and 4, are they on the same side or opposite sides? They're on opposite sides. So wedge, dash. Now I ignore the fact that 1 and 4 are even there and say, okay, 5 and 6, same side or opposite side? Opposite, right? So, right. So what I'm doing is I'm just having you do the relative stereochemistry on 1 and 4, the relative stereochemistry on 5 and 6, but I'm not having you try to figure out the stereochemistry comparing 1 to carbon 6. So I'm having you do the stereochemistry from the diene by itself, the stereochemistry from the dienophile by itself. So that means that you could have also written that, and that would also be correct, right? Even though they're different molecules, but the relative stereochemistry between 1 and 4 is correct, and the relative stereochemistry between 5 and 6 is correct, but we're not worrying about comparing carbon 1 and carbon 6. It's too hard. I learned how to do that in grad school, if you really care that much. 6 greatest years of mine. No, I can't even say it. So you could go do that if you wanted. But so what we're just going to do is I'm going to have you pretend that 1 and 4, do that. 5 and 6, do that, and that's good. As long as they're both right, the whole thing will be right. As long as the relative stereochemistry of 1 and 4, and then 5 and 6 are right, we're good. So this next one, draw a theme. It's going to be blue. So groups on 1 and 4, same side or opposite side? Same side. So we'll wedge them both. Groups on 2 and 3 just end up being on 2 and 3. Nothing fancy, no wedges or dashes. Groups on 5 or 6, same side or opposite side? Same side. So again, pick one. I like wedges. If you like dashes, equally cool. And that'll be your product. Where you could have groups kind of on every position that can give you stereochemistry.
I was asked if the top dienophile would do a Diels Alder reaction because the two groups are cis.
I can do the top one. Why do you think you can't do the top one? So that's only on the diene, right? So only the diene are you not allowed to have the two groups inside. But here, right, this and this, even though they do bang into each other, double bonds can't rotate. So there's no way for them to get away from each other. So you are free to have groups on the same side of your dienophile, but not on your diene. That make sense? Okay. I saw head nodding. It was all good. Okay. So I'm going to draw out my ring. So the thing that I kind of do that we effectively cheat on is what I have you do is I have you worry about the stereochemistry on carbon 1 and carbon 4. Ignore 5 and 6. Just the groups on 1 and 4. They're going to be on the same side or on opposite sides. Same side. They're both outside, so they're going to be on the same side. Now, I have you pretend that carbon 1 and carbon 4 don't exist. The stereochemistry on 5 and 6. The ketone, is it going to be on the same side or opposite side from the ethyl group? Same side. So my ketone, my ethyl group will be on the same side. Then my ketone and my methyl group will be on opposite sides. It's doable, but difficult to get your stereochemistry between carbon 1 and carbon 6 right. So I just don't have you worry about it. I have you basically treat, this is where I just put my hand over something, but I can't do that electronically, right? I have you treat 1 and 4. That stereochemistry is wholly independent from 5 and 6. And I have you treat 5 and 6 like 1 and 4 don't have any influence on it. In reality, there is, but go to grad school, right? I learned that in grad school. It seems like a good place. So if you care that much, talk to me about going to grad school. It'll be great, right? So, so we're always just going to worry about the relative stereochemistry between 1 and 4, then the relative stereochemistry between 5 and 6, but we're not going to worry about how 1 and 4 relate to 5 and 6. Oops. Okay. Groups on 1 and 4, same side or opposite side? Opposite side, right? One's inside, one's outside. So I'm gonna wedge and dash. Five and 6. Nitro group in the nitro group on 6, methyl group on 5. Same or opposite? Same. And then the two methyl groups are going to be on opposite sides. There you go. I did forget the methyls on 2 and 3. Don't do that. Be better than me. The student becomes the teacher. I mean, you are wearing a shirt right now, so I didn't have to kick you out. That'd have been awkward. We can also have more than one group on the dienophile, on each carbon of the dienophile. And we're going to do effectively the same thing we did before, right? Which is we're just going to have to compare to the groups we already have. So, groups on 1 and 4, same side, opposite side. Opposite. We got 1. So now, we compare the ketone on 6 and the ethyl group on 5. They're on the same side, right? So I can just put them on the same side. And now I can say, okay, the ethyl group on 5 is on the opposite side from the methyl group on carbon 6. So if I put that ethyl group down, that means the methyl group on carbon 6 has to be up.
I was asked to re-explain the stereochemical outcome on carbons 5 and 6.
Sure. So if you look at the ketone on 6 and the ethyl group on 5, they're on the same side, right? So they have to be on the same side in the product. So I decided to put them both down. Now to figure out where the methyl group is on carbon 6, I can say, okay, it's on the opposite side from the ethyl group on carbon 5. So that means if the ethyl group on carbon 5 is a dash, is down, that means the methyl group on carbon 6 to be on the opposite side has to be a wedge and up. That makes sense? Excellent. All right, so carbon, groups of carbon 1 and carbon 4 are both outside, so they're both on the same side. So I'll put those up. And then the nitro group, we'll see it's up. Right, so it's on the same side as the methyl group on carbon 5. That makes the methyl group up. Now the nitro group's on the opposite side from the isopropyl group. So if the nitro group is up, the isopropyl group is down. So far, so good? All right. So something you may or may not have noticed as I was going through is in every one of the examples I've given you, one of the two pieces, either the diene or the dienophile, are symmetrical. Right? So if you look at this, there's a plane of symmetry right here. This one is not really symmetrical, but on either side you have a methyl group, right? You're going to get the same thing. If I go back, I think there's one where I have made the dienophile symmetrical. I think. Maybe not. Ah, here we go. Right, that's symmetrical. The reason I did that is because it doesn't matter how they approach each other. If one of the two pieces is symmetrical, you can only ever get one product, right? But what happens if neither the diene or the dienophile is symmetrical? So let's say we have this diene and this dienophile do a Diels Alder reaction. They can react the way I have them drawn, right? And you end up with, right, your methyl group is on carbon 1 and your ketone's on carbon 6. But there's nothing keeping these two molecules from flipping over and reacting in a different orientation, right? So what happens if my diene flipped over and was oriented like that? Now, when I get my product, now my methyl group is on carbon 4, right? Okay. So now I'm getting two totally different products from the same starting materials, right? And if I really want a group on carbon 1 and a group on carbon 6, I don't want to have to throw away half of everything that I make because half of it is the methyl group or my substituent on carbon 4. So how can we kind of predict what products we're going to make and control what products we're going to make? So So if we add something called an electron donating group to the diene, it templates how the diene and the dienophile are going to react. So you can predict how they're going to orient themselves every single time you do a Diels Alder reaction, and just so happens to speed up the reaction as well. So you get more control over your products and your reactions are easier. So what are our electron donating groups? So ethers, where the R is methyl, ethyl, propyl, kind of whatever. As long as you have an oxygen singly bonded to the double bond of your diene, it's going to be electron donating group. Amines, normally just tertiary amines, but amines will work. And then thioethers. Thio is the prefix for just sulfur containing. So instead of an oxygen ether, it's a sulfur ether. And sulfurs basically just do everything oxygens do, but they smell worse doing it. All right. So how do these electron donating groups work? What are they doing? How are they allowing us to predict our reactivity? So I'm going to just use a simple ether. Right? And we can predict what's going to happen because of resonance. So I've got this lone pair on this oxygen. And I can push down and push electrons out on the double bond. So I have an atom with a lone pair beside a double bond. I can draw a resonance structure. So I end up with this oxygen with a double bond. And now I can take that. I have a lone pair or I have a negative charge beside a double bond. So I can draw another resonance structure. These electrons can come down, push those out. All right, so I can draw these two resonance structures. The one that really matters this last one is the one that's the most important for the Diels Alder reaction. It's the one we care about the most. So because of that, what we end up saying is that if I have a group on carbon 1, electron donating group on carbon 1, carbon 4 is going to be partially negatively charged. Now, in all actuality, carbon 2 is also partially negative, but the fact that it's partially negative doesn't impact the Diels Alder reaction. So we really only care about this last resonance structure. Right? So we can generalize this to just say any electron donating group on the end on carbon 1 is going to make carbon 4 partially negative. So why do we care? So if you remember when we talked about dienophiles, we said, oh, to make the reactions better, right? We put an electron withdrawing group on our dienophile. What that does, if you remember, is it makes the carbon on the opposite end of the double bond from the electron withdrawing group slightly positive. And now your electron donating group on your diene is making a carbon slightly negative. So your negative carbon wants to bond to your positive carbon. So you know that your diene and your dienophile are going to arrange themselves in such a way that you're going to always make a bond between the negative carbon and the positive carbon, right? So they're going to be attracted together. It's going to hold the diene and dienophile so that you only are ever going to get one product. So in this case, 3, 4, 5, 6. So in this case, you're only going to get the product where carbon 1 and carbon 6 bond together, or carbon 4, which was negative, bonds to carbon 5, which was positive. And that's the only product you're going to get. So now we can pile all this stuff we've been doing on top of each other, right? So I think the first thing you want to do is figure out which carbon is negative and which one's positive. So which one's negative? Hmm? So carbon 1 has a donating group. That means that carbon 4 is going to be negative. Which carbon's positive? 5. So these are going to react just like I have them drawn. Carbon 4 is going to bond to carbon 5. So the nitrogen on carbon 1 and the methyl group on carbon 4, are they on the same side or on opposite sides? Same side. So they're both going to be on the same side in the product. So we make the nitrogen up. That makes that methyl group up. Right? And then the nitrogen on 1 and the ethyl group on 4 are on opposite sides. One's outside, one's inside. So if the nitrogen's up, the ethyl has to be back. Now, the amide on carbon 6 and the methyl on carbon 5 are trans, they're on opposite sides. So that means that they are on opposite sides. One's a wedge, one's a dash. I always think it's important to identify your positive and your negative carbons first so you know how things are going to be oriented to react, right? So carbon 4 here is negative and carbon 6 is positive. So they're not going to react the way I have them drawn, right? Because carbon 4 wants to bond to carbon 6. And the way I have it drawn right now, it's not going to happen. So what I like to do is I like to flip usually the dienophile over, leave the numbers the same, but I'll just flip it over and say, okay, 5 and 6. So this is how these two, the diene and the dienophile, would react with each other, right? So I'm going to redraw the diene. So it would react like this. So now the negatively charged carbon 4 is going to bond to the positively charged carbon 5, carbon 6, positively charged carbon 6. So this means that when you draw your product, 1, 2, 3, 4, 4 bonds to 6, 5 bonds to 1. And then you fill in your groups. Oxygen and methyl are on the same side. The nitro and the ethyl group on the dienophile are on the same side. So again, they could be on the same side. It could be dashes are on the same side. And now the nitro on 5 and the methyl on 6 are on opposite sides. Yeah. So the way you know that your carbon 6 or whatever is partially positive is you identify your electron withdrawing group, right? And then what the carbon on the opposite end of the double bond from that electron withdrawing group is always going to be partially positive. So you have to remember your electron withdrawing groups from on Friday when I was like, here's a list of all your electron withdrawing groups. So you have to remember those so you can look at your dienophile and go like, oh, that's my electron withdrawing group, opposite side is positive. Make sense? Excellent. The electron donating group doesn't always have to be on carbon 1 or carbon 4. It could also be on carbon 2 or carbon 3. If your electron donating group is on carbon 2, it can only push electrons to the opposite side of the double bond it is on. Right? It can't interact with the other double bond. So we can say, hey, our electron donating group is just going to make the double bond, the end of the double bond it's on, negatively charged. That makes sense? So in general, any electron donating group, if it's on one of the middle two carbons, it just pushes electrons to the opposite side of the double bond that it's on. So if you had like your electron donating group down here, the end of the double bond it's attached to ends up being negative. So which carbon is negative? 4. Which carbon is positive? 5. Thankfully, the way I have it drawn, right, carbon 4 wants to bond to carbon 5, and that's how it lines up when you draw it, or as it is drawn. So this is just like all the ones we did before. Carbon 3 has the nitrogen. No stereochemistry on a double bond, just flat. The two ethyl groups on 1 and 4, same side or opposite side? opposite. So we'll wedge one, dash the other. Ethylon 1, methylon 4 are on the same side. So put that methyl group on a dash, on a wedge. Words are hard. So then ketone on 6, ethyl on 5 are on the same side. So we can wedge them both. And then methyl group on 5 is on the opposite side from the ketone. So that'll be down. Which carbon is negative? 1. Which carbon is positive? 5. So the way I have this drawn right now, this isn't how they react. So I want to flip over the diene, or the dienophile. So they're going to react like this now, where this is 6 and 5. Now I'm flipping these over because I think it helps you see what's going on, but you don't have to. So you could just leave it as it's drawn and just get your numbers right. And say, oh, I know that one wants to bond to 5. So these are on opposite sides. I have no fever. I'm fine. Don't run. So we just kind of built our way up from knowing what the Diels Alder product was going to be, adding all the stereochemistry, and now predicting how they're going to go together. So Wednesday we'll do cyclic dienes and some nomenclature stuff, and probably finish off diene stuff either Wednesday or early Friday.
I was asked if you could switch the stereochemistry on 5 and 6 in the last example.
Absolutely. The only thing that you know is they're on opposite sides, so you can switch them. You could have 6 dash 5 wedge. That's fine.